Good morning, everyone. Can you see the screen? I have shared the screen. Can you see the article now clearly?
Yes, sir. Yes, sir.
Okay. So I have just discussed only one paper in the last class, and I have taken too much of your time because it was the first discussion with the papers. So I had to tell you some of the important facts related to the article. Okay. So with continuation of that, we'll be dealing with some other articles which are important findings to them. Okay, and they have shown that what are the idea that you have already learned, how they can be applied or they can be understood with the laboratory or the field experiment. Okay, most of them are the laboratory experiment studies, and so we'll be and there are some simulation and the modeling studies, and we'll be doing very brief on the theory because you have already read that, and then we'll be discussing mainly the results part. Okay, so in the next I am going step by step papers. Okay, the serially going through the papers. So in this category, this is the another one good paper which is done by Clarkson and his group, Clarkson, Bastin and Levy. Okay, now this paper discusses about the monolayer and the adsorption, different adsorption theories on the monolayer and the multilayer adsorption, and what are the variations of temperature and pressure with this adsorption. Okay, now for this they have done also the powder sample. Okay, and with the powder sample they have taken both the low pressure adsorption and also the high pressure adsorption. Okay, the low pressure adsorption is done generally with the nitrogen and CO2. Okay, at a very low pressure, means 0.127 megapascal. So it is only 127 kilopascal, very low pressure. This low pressure adsorption of nitrogen and carbon dioxide, these are particularly done for pore side distribution. Okay, you know that there are different sizes of pores. Okay, the micropore, mesopore and the macropore. So this nitrogen adsorption and the CO2 adsorption are going to show you how much the pore network is there, how they are distributed, what is the fraction of the micropore and macropore and the mesopore. In these three category, if you are going to use CO2 micropore adsorption, it can read up to less than, very much less than 2 nanometer range. So it will cover most of the micropore. Whereas if you are going for the N2 adsorption, for N2 adsorption, it cannot give the good results below 5 nanometer. Okay, so N2 adsorption, low pressure N2 adsorption, this is not performed for the micropores. Generally, it is performed for the mesopore and the macropore. Okay. Now, the different methods, these two different methods, detailed discussion is not required for you. For your case, it is sufficient that this low pressure N2 and low pressure CO2 adsorptions are done for the pore side distribution. Okay, and what is the limit of the adsorption? What is the limit of the size range? That will be sufficient for you. Okay. Now, let us come to the background, what they have discussed. In this background, they have first discussed about the normal adsorption model. You can see this is the Langmuir model, what you have already learned about this. This Langmuir model and this Dubinin theory of adsorption of vapors in the micropores. Dubinin theory of adsorption potential, the items, the parameters may be somewhat different than whatever you have learned, but the form of these equations are same as we have seen in the note, in the background note. Okay, if you see the background note, you will be able to see that the Dubinin-Raduskevich equation and the Dubinin-Astakov equation, these two are present there, and they are based on the Polanyi's adsorption model with the adsorption potential theory and the volume of the pore filling. Okay, so this theory are not, I'm not going to discuss again. And then next is the BET equation. Okay, what is the BET equation? Now the BET equation is the Brunner, Emmett and Taylor equation. Okay, you will be able to see this is the BET equation. So they have taken three different concepts and 4 different equations. First is the Langmuir concept with Langmuir equation. Second is the BET model with that BJH or BT equation, Brunner, Emmett and Taylor equation, okay, which is valid for the multilayer based on the concentration gradient. And third concept is for the Dubinin theory, and with the two different equations, Dubinin-Raduskevich and Dubinin-Astakov equation. The main difference between this dr and dA equation is that there is a component, there is a quotient in this Dubinin-Raduskevich equation. This n is taking a value of 2, whereas in the Dubinin-Astakov equation it is taking a value of n. So in dr equation there are three unknowns, W0, two unknowns, W0 and varying with T, you will be able to get that T0 is a saturation vapor pressure. You have to calculate. Whereas in Dubinin-Astakov equation, you have to calculate the W0, this N, and then there are other parameters of E, absorption potential, you will be able to calculate. Okay. So based on these equations, they are going to do the modeling. So this is for the absorption model. Later, what they have done, they have taken samples, okay, total 13 samples are taken, okay, from different coal mines, okay. These are the coal samples, and they are done under the high pressure absorption, methane absorption analysis, okay, and based on the powder samples, okay. And the category, the different information of these samples can be shared here. You can see that the proximate analysis results are also given, okay, and these are the materials, okay. The petrographic analysis, percentage of volume percentage expressed in volume percentage, and MMF means mineral matter free, okay, mineral matter free, okay. And this proximity analysis are given as in the percentage only, okay. So volume percentage. And if you see the ash percentage, if you see the ash percentage, you can see that most of the cases the coal samples are of very good quality. Only some 2 or 3 coal samples are having more than 15% of ash. So you can understand what is the quality. Whereas generally for all the coal samples, the fixed carbon are staying more or less in the same category. As you can see from this table, the fixed carbon content is more or less same, whereas the moisture is somewhat higher side for 2-3 samples, but the ash percentage is varying totally from as much as less than 3 to high as 30% or 33% or 10 times variation, okay. And these are the measurables, okay. Now with this sample information, okay, first let us see how this absorption are going to vary. So this is the absorption graph. This is the absorption graph. You can see this, okay. This is for the same sample. You can see the legend of the figure, Langmuir and BET graphs. This AB is for the Langmuir and CD is for the BET graphs for 2 samples, okay. These points, the bullets are the experimental data and the lines are the modeling, okay. And you can see that the nature of the graph between this Langmuir and this BET are different. If you remember the different 6 types of the absorption isotherm graph, this Langmuir graph is the type 1, whereas the BET graph is for the type 2, okay. And here also you can see the volume adsorbed is expressed in cc per gram, okay, centimeter cube per gram at STP, standard temperature and pressure. Standard temperature and pressure is assumed here. I have also mentioned that 15.5 degree centigrade, which is coming as 278.5 Kelvin, and obviously the atmospheric pressure, and these are expressed in DAF basis. So remember the concept. Earlier they have shown the sample information based on the mineral matter free basis. This is mineral matter free basis, okay. And then they are showing the results in the DAF basis, okay. And these are the comparison. This is for the methane and this is for the BET. You can see that definitely, although the maximum reach of this absorption are more or less same, you can see this is also experimental, this is also showing maximum as 20, this is also showing maximum of 20, but depending on the modeling, the lines or the graphs, okay, are going to vary a little, okay. Langmuir absorptions are going to attain the equilibrium,
whereas BET equations are still increasing. Okay. Next observation for this figure is for the carbon dioxide. You can see for the carbon dioxide how much they have taken, and this cell pressure is given in the kPa. This kPa, you can see, this is for the low pressure adsorption studies for CO2 adsorption. Okay, very low pressure. You can see kilo pressure, kilopascal, only 50 to 200. Okay, this is the variation. This is for the micropore adsorption. Whereas these earlier examples are in the MPa from 0 to 10 megapascal. So please look at the units also. Okay. Okay. So you can see here that the whatever exponential letter you are getting, it can be easily fitted by the Langmuir graph or the BET graph. Okay. Next is the residuals. Residuals means the error from the mean. For all these examples, whatever you are going to fit by the BET equation or by the Langmuir equation or by the DRDA, you can see that A, B, C, D. A is the for Langmuir, B is for BET, C is for DR, and DA equation is given by D. These are the residuals. Residuals means the error from the mean for 4 type of modeling equations. Okay, obviously you can see that for Langmuir, the Langmuir and BET, the graphs are varying. The high range. Okay, for DR it is of low range, and obviously for DA equation, this is very much accurate because there is a no variation from the mean. So in this case, you can say that probably the DA equations will be better for the adsorption modeling. Okay. Next, they are going to relate this. They are going to relate this with the same residuals they are going to plot for different samples, and finally they are going to relate it with the various Langmuir volume and the Langmuir pressure. You can see here these are the Langmuir volume. Okay, you can see the monolayer or the micropore volume, Langmuir volume, and the BET volume, whatever they are going to get from here. And this is the average relative error they have taken. The average relative error is given by this equation. This is the equation. Okay, this is the equation for average relative error. You can see where 100 is the 100 by n. N is the total number of the observation. Sum of absolute V calculated minus V experimental divided by the V experimental. This is the standard statistical concept for average relative error. Okay, so you can see these are the values, and obviously you can see if you compare the values, you can see the Langmuir values are more or less higher side, whereas DA values, the error values, are very much on the lower side, and this is the average value. Okay, so now you can see that for various models, DA are more or less the best fit. Okay, and then they have discussed each of the correlation here. The next point which I wanted to show you is the temperature variation. You can see that in this case, the temperature is varying from 298, 303, and 323. Okay, these are in the absolute scale. And with this, for a particular sample, how the volume is absorption is going to vary. You can see, obviously, you have already learned earlier that an increase in temperature is going to reduce the volume absorbed. So here also you can see for small bullets, you can see the small bullets are 298 Kelvin, and they are going to show you very high absorption. 303 Kelvin is very much close to it. Okay, and then the lowest absorption values are going to be suggested, going to be exhibited by the highest temperature, 323 Kelvin. So obviously, until unless you have seen some results, you cannot validate, you cannot comfortably say that, okay, whatever we have learned, this is final. But now you can see that whatever you have learned earlier, and there are papers which is going to complement that, which is going to support that idea. So now you can take the conclusion that, okay, that with increasing the temperature, the volume is going to decrease. Okay. The next is the characteristics equation. The characteristics equation is a property for Polanyi's theory. You can see here that in the y-axis, the volume absorbed is measured here. You can see here the basis is changed here. It is the raw coal basis, not DAF, not MMF. Raw coal basis means as residue basis. Okay, and then you can see here also if you see the x-axis, in the x-axis they are going to show you the adsorbed potential A, which is the function of R, universal gas constant, T, absolute temperature, P0 is the saturation vapor pressure, P is the experimental pressure, and this is expressed in terms of joule per mole, work done per mole. Okay, and obviously they have also shown here the variation with temperature. Okay, so this is the graph for absorption potential. You can see that for methane, all these graph for a particular sample, okay, for this particular sample GHAI 09, T0 is calculated with the vapor pressure, okay, extrapolated vapor pressure, and then the graph is prepared here to show only for one sample, okay. Now this is for methane, and then this is for the, this is also for the methane, okay. But then you can see for methane the graph is more or less on the very much milder steepness, okay. So it is not very steepy, and it is going to take consider, it is going to express within the 0 to 15,000 joule per mole, okay. You can see the x-axis variation and the y-axis variation, the range, okay, and the y-axis, all of them are showing from 0 to 0.5, okay. These are for the methane, obviously. This graph and the next graph, this is also for the methane. But if you come to see for the carbon dioxide, if you are going to see for the carbon dioxide, let me show you. Yeah, this is for the carbon dioxide, okay. Now you can see that the y-axis variation is much more less, and the carbon dioxide graph is not very much spreaded, okay. And here you can see that although the graphs are more or less having the same variation, it is more or less superimposed based on this two line, okay. Whereas in the methane graphs, if I show you earlier, this is for the methane graphs, you can see that for methane graphs some of the differences are observed, for this characteristic equation. In these two graphs, and also in this graph, you can see that they are, here the deviation is much less, whereas in this graph you can see there is a little bit deviation for the absorption potential and the volume adsorbed, okay. So you can also see that there is a difference in the methane and the carbon dioxide absorption potential. For this carbon dioxide, you can see there exists some values which is going beyond 15,000, okay. And this spread is more or less, it is going to be very much milder at the higher absorption potential, but lower the steepness, the graph becomes steeper, as well as whenever the absorption potential is going to decrease, the graph is going to be steeper than the milder, okay. And depending on the range, there is no such variation, although the range is very much differentiated. Some values are not existent, not found more than 0.015, I can say, at high temperature. So what is the observation? That there exist some definite differences of the absorption potential for methane and carbon dioxide, okay, depending on this volume adsorbed, depending on this temperature, and depending on this pressure, whatever pressure you are going to apply, the experimental pressure, the adsorption potential can vary from 0 to more than 15,000 for carbon dioxide for a particular sample, or it can vary from just 0 to a little bit of 12,000 or so, okay. And see, these data points, the data points are equally distributed, okay, and the values. So although the conclusion is that although you are going to consider the same temperature and pressure to calculate the characteristic equation, the volume adsorbed are different for methane and carbon dioxide, and also that if you change the temperature, the graph is little bit varied for methane, so the characteristic equation is changing for the methane but not significantly for the carbon dioxide, okay. These are the observations, if you can see from here, okay. And if you read the conclusion of this paper, they are also going to discuss the same concept, If you see the conclusion, yeah, this is the conclusion. They are going to discuss the same discussions whatever we have observed here. Okay. So let us go to the next paper. Okay. Next is the 99 and to Clarkson 99.2. Okay. And again, I am telling you that for this particular case, you don't need to have a very good idea about what theory they are going to discuss. Okay, this is I am going to show you just to give you some idea, about the research system. Okay. Now this is the another paper, another good paper. What they are going to do here? Okay, they are going to do the pore structure and variation of the gas pressure. Okay, how the pore structure is going to affect the transport. Okay, and here they are going to find out the absorption rate modeling. Absorption rate modeling means with time, how with time the methane and carbon dioxide absorption is going to take place, and they are going to model the data. Okay, so they are going to take the same absorption results whatever they have taken earlier. Okay, and here there is no particular experiment. This is the calculation part only. Okay, now for here I have never discussed with you about the absorption rate modeling or the diffusion modeling, but I am introducing this very briefly to you at this paper. In this paper there are two types of absorption rate modeling. There are diffusion modeling, two types. First is for the unipole modeling. Unipole modeling is going to consist, you can see here that they are in this paper, they are going to discuss what is the unipole modeling and what is the other bi-disperse pore modeling. You know the diffusivity or the diffusion rate. Okay, how it is going to vary, you know about the diffusion. The unipole modeling is going to show you, it is going to assume you that the pore structure within a coal sample is homogeneous. It is homogeneous and it is more or less there is no variation. Okay, and whatever the diffusion is carried out, you can see here whatever diffusion is carried out, it is obviously in the isotherm condition, because absorption is going to be governed by the isotherm condition. So these are the assumptions. So they have proposed this infinite series. Okay, exponential powered this series, this d here is taking care of the diffusion, and diffusion or diffusivity, which is the d by r square. This rp square is the length about the particle, length of the particle, how much they are going to move from one point to another point. This the d by r square is considered as the diffusivity, or sometimes the d itself is going to show you give you the idea about the diffusion rate. Okay, or diffusion, sorry, not the diffusion rate, the absorption rate or the diffusion. Here you can see that this is the fundamental partial differential equation for the diffusion, with having the terms of diffusivity d by r square. Okay, and c is the concentration, t is the time, r is the distance between the particles. Okay, r is the radius of the particles, how much it is going to travel. And then you can see here that this equation 2 is going to be expressed as mt by m infinity. Mt means at any point of time t, how much is the mass is transferred with the infinite time ratio, with the infinite time. Infinite time means at the equilibrium. At the equilibrium, how much mass is absorbed is going to be given by the m infinity. And mt is the mass transferred or absorbed at particular time t. Okay, and how to take time t? When you are going to channelize some gas from the reference cell, the moment the absorption is going to be started and the pressure gauge reading in the sample cell is going to start decreasing, that time is going to take as 0, time 0. You put the stopwatch, and then with afterwards you are going to take seconds as 1, 2, 3, 4, and you are going to take the data. Okay, so you will be going to take some pressure data. Later in this equation 3, they are going to divide this mass and they are going to replace this mass with the volume uptake, because for the particular coal the density will be same as the temperature is going to vary. So the density may change, but if you are going to consider the volume and the mass at the particular sample, then obviously whatever changes with the density, that will be going to be nullified because of the same sample. So that's why they are going to change this MT M infinity ratio to Vt by V infinity, the volume at time t and the volume at infinite or equilibrated time. Okay, and this is the infinite equation. Okay, this is called the unipole model. This is called the unipole model, but this equation is there are several problems, there are several advantages and disadvantages of this model. This is very simple to use, and this is always give you the first approximation. You can see that for Vt by V infinity 0.5 less than 0.5, that means if you're within your half intake of the total equilibration time, of the total ends up time, the equation can be approximated by equation 4. Okay, and so after that it is going to deviate. The problem is that after that it is going to deviate. Okay, so if you see the unipole model, you will see that after some time the unipole model is going to deviate from the exponential model. Okay, and so obviously there is lies some problems with the unipole model, because the concentration dependent, okay, it is going to increase. The parameter, the diffusion parameter is going to increase with the concentration. Okay, and as the concentration is going to increase, the diffusion rate is also going to increase, because diffusion is very much concentration dependent. Okay, but then it is observed that if this fast approximation, it is going to be given a linear variation, but it may not be expressed by a linear, because the adsorption is not happened in a linear fashion. Okay, that's why this is the problem of this unipole model, and so the concept of bidispersed model are coming. What is the bidispersed model? In the bidispersed model, they are going to have defined pores, micropores and the macropores, two extreme. Mesopore is not considered. Micropores and the macropores, both of the pores are going to give individual shares for the diffusion. And so, depending on the size of the pore, the diffusion rate in the micropore and the macropore are going to be different. So, they are proposing, it is proposed with the equation. You can see the equation is going to, they have not given the equation. There is a definitely different equation. If I show you, let me show you a glimpse of it. There lies different equation for the micropore model. Okay. If I show you this, yeah. Yeah, this is the unipore diffusion model, and this is the micropore diffusion model, macropore and macropore. This is the bidispersed pore model. Okay, this is going to take within the micropore and the macropore. So the pore structure is assumed to be heterogeneous here. Okay, and then again same isothermal conditions will be prevalent, and then it will be given, it will be expressed by this equation. Okay, where you can see one part is having for the dA and one part is having for the dm. The
Sorry,
dA
screen
is
is not shared, sir.
okay. Sorry for this. Let me just share the screen also. Screen, yeah. Now it is visible.
Yes,
It
sir.
is visible. Yes. So what I am telling, that the bidispersed diffusion model is going to be expressed in this equation. There is a very long equation. Why this long equation? Because it is going to be composed of two different parts. One is taking care of the micropore part, the dA and dm. Okay, sorry for this same nomenclature. The dm is for the micropore and the A is for the macropore diffusion. And this is the total equation going to be taken care. And for each of this dA and dm, this is the transcendental equation. The transcendental equation is very much complex. It cannot be solved directly, but it can be solved only by the iteration. Okay, it can be solved by the iteration process. So this is the transcendental equation, because you can see you have to calculate the lambda, but the same lambda is also a variable within the trigonometrical expression. Okay, So just like the theta and sine theta, you are giving an equation and then you have to calculate both theta also. So you will be able to, you will be not able to solve them directly. Okay. So this is the concept of this bidisperse pore modeling. Okay. But then what is the disadvantage of this? Although it is going to take the very much accurate heterogeneous model, because the pore modeling is having both the micropores and the macropores, but then the problem is that it is very much complex and very much iterative solutions are needed and very much time consuming. Obviously you can see it is very much time consuming, but then this modeling is very useful for diffusion modeling. Okay. So now with this they have taken both the Langmuir modeling, and what they have done in this paper, they have done some various numerical calculation to take the different bidisperse pore models. Okay. They have done the simulation for both unipore model and the bidisperse model. Now, whatever these two models I have shown you, these are the fundamental unipore and the bidisperse pore modeling. But in this particular paper, the Clarkson and group, okay, Clarkson and Bastin, they have done this numerical simulation with the partial differential equation, using the partial differential equation and one dimensionless parameter. They have done the unipore analytical model and the bidisperse analytical model, and they have shown the fit. They have shown the fit with the experimental data. Okay, and they have given the results. These are all the unipore fit. You can see that the fractional aptitude is varying from 0 to 1. The moment it is reaching 1, it is going to be straight line, because the total percentage is going to be fitted. The total percentage is going to be absorbed. So no further, it cannot be taken more than 1. Okay, so 100% absorption is taking place, and so it is becoming flat. These are all the data for the unipore modeling. These data are showing you the square root of time with the density, how the density is going to change. The density is going to reduce. So the gas which were packed earlier, now with increasing time they are becoming lighter. Why? Because the packing, as the diffusion is progressing, so they are not becoming concentrated. They are becoming very much lighter. They are becoming very much diluted. That's why the density is also becoming lesser. Okay. Now, these are for the unipore models and these are for the bidisperse pore model. Okay, let me show you here. Yeah, this is the bidisperse pore modeling. With these are some of the parameters. You can see here the diffusion, unipore diffusion model data. They have calculated the diffusion with the pressure. Okay, you can see d by r square is given here. And finally, with the bidisperse pore modeling, okay, they have also shown what are the input parameter, and this bidisperse pore modeling, these are the results. So you can see that the bidisperse pore modeling are going to explain the experimental data much accurately than the unipore modeling, because you can see almost the experimental data and the modeling data are very much superimposed. Okay, so these are the gist of this experiment. Okay, and these are the data. You can see that for all the samples they have calculated for the dry, for the moisture, and for the dry experiment with the carbon dioxide and methane, they have calculated both the macropore and the micropore diffusivity. These are the diffusivity, okay, per second for both methane and micropore, methane and carbon dioxide. And obviously you will be able to see that for methane, the diffusivity values are sometimes are generally lower than the carbon dioxide, because the rate of carbon dioxide is higher. The adsorption rate of carbon dioxide is always higher, because the adsorption is always higher for the carbon dioxide than the methane. You have seen earlier case that the ratio is always higher and it is varying from 1 to 2 to more than that. Okay, so the diffusion also, it is supposed to be higher for the case of the carbon dioxide, where at some point you can find that some irregular observation is also found. But here, as you can see here, all the carbon dioxide diffusivities, micropore and the macropore, these are in the terms in the order of -3 to -2. Okay, whereas for methane, the diffusivity found here, you can see that it is in the order of 4 and 5. So obviously here also the carbon dioxide diffusivities are much higher than the methane diffusivities. Okay. Now, if you read this, you can find the comparison you can find the comparison between the unipore and the bidispersed pore model. But other than this, whatever you have learned, whatever I am giving you, you can see it in the conclusions also, that how much diffusion is going to vary for these two cases, and how it is going to vary the pressure, how much the ratio of the diffusivity for this methane and carbon dioxide they have discussed here. And you can also see in this graph, that the diffusivity is also supposed to be increase or decrease based on the adsorption and the desorption. You can see here for some particular diffusivities, okay, you can see that sometimes it is going to increase with the pressure, sometimes it is going to decrease with pressure. Whereas the numerical modeling showing that it is going to increase, the numerical modeling is showing that it is going to decrease. Okay, so there lies some confusion also, but still, because it is very much complex with the macropore and the macropore conditions, but still these fundamental pore models, unipore and the bidispersed pore models, are used everywhere for a fast approximation to get the value of the diffusion, so that you can calculate the absorption rate, how much quickly the gases are absorbed. Okay, this is the gist of this paper. In the next paper, I'm going to show you for OSDME 2003. Okay, this paper is going to give you some different modeling concept than the Langmuir and the Polanyi's model, or on the BET model. Okay, they have also shown that theme of this paper is the volume effects on the absorption isotherm of carbon dioxide. Okay, now what they have done, they have also taken, they have first expressed the void volume here. If you see the sample cell, this is the schematic diagram of the sample cell. When you are going to put some gas into the sample cell, obviously there is a coal, and obviously this is the absorbent. Absorbent means the one who absorbs. Here it is the coal, and the absorbate is the gas which is being absorbed. Okay, so whenever you are going to put some gas into the adsorbate, so obviously the gases will be coming here, okay, and some of the gas will remain in the free phase, some of the gas will be in the adsorbed phase. Okay, now you have also seen earlier that most of the cases we are going to neglect the adsorbed phase in the sample cell, in the void space of the sample cell, and so we are going to get the excess adsorption. But here they are going to neglect that adsorbed phase, and then they are going to consider that adsorbed phase, and they are going to calculate that what is the change of the adsorbed values for these two different conditions, and they are going to show us this. Okay, if you see the results from the experimental pressure, the deviations of this, and they have also given the different models. These are the different models. Okay, these are the different models used for this. Okay, you can see the monolayer surface absorption model for Langmuir, and then Toth and unilayer model. There are different models. For multilayer, there is a modified BET equations, and for pore filling, there is a Dubinin-Nastakov equations. Okay, and these are the data of the coal proximity analysis and for the ultimate analysis. The schematic diagram is more or less the same concept. Okay, but the results, yeah, this is the results. Okay, you can see here for this volume, okay, for this volume, some of the volumes are different for as received and the dried at 80 degrees centigrade. If you are going to dry the sample, so obviously the moisture is going to evaporate, so obviously it will show some higher specific pore volumes or higher specific volumes of the coal. Okay, this is the result. For here with the carbon percentage, they are going to calculate the density. So here also you can see they have utilized different equations to calculate the density and see the variations. Okay, here in this third graph, they are going to show that the figure number 5, they are going to plot the adsorption, the volume of the shrinkage. Shrinkage, I have also discussed with you that during adsorption, the volume will increase, it is swelling effect, whereas during desorption, the volume will decrease because the pore pressure is going to release. Okay, so they are going to measure here the shrinkage effect also. Okay, so with moisture, and if there is any loss of the moisture, and how the moisture loss is going to differ, going to be significant in the volumetric shrinkage, they are going to plot. So you can see here, if the moisture loss is very high, the volumetric shrinkage is also very high. Okay, the more water is going to release, the more is the contraction of the coal. Okay, and this is the shrinkage they are going to calculate by this formula. Okay, now the other graphs what they have discussed, yeah, this is the graph. You can see the absorption and the desorption graphs first they have expressed. Okay, and these graphs you can see that for the Pocahontas, for the first sample, this is the graph for Langmuir. Okay, these are the Langmuir graph. Okay, the experimental graph, and all of these are the x's. This is also x's, this is also x's graph. This is from the BET. Okay, okay, now here you can see that for the first case it is nearly superimposed. For the second case there is a little bit gap. The third case there is a much more gap. So this gap is called the hysteresis. Okay, for depending on the some coal type, it may be present or may not be present for the same temperature and the pressure condition. And you can see here, these are the same argon premium coal, Pocahontas and the white oak coal and the Grand Canyon. These are the same coal which is being used in the bush work. Okay, and then they have fitted experimental data with the modeling, and these are the modeling and these are the deviations. You can see here. Okay, various parameters, various equations has been fitted, and they are going to show the deviations. Okay, let me zoom it much more. Yeah, now you can see there is a very and the hysteresis is absent. This is little hysteresis, and this is much higher hysteresis, and these are the variations of different model to show you which are the best fit model. Okay, and obviously with this they have calculated the errors. These are the errors you can see, and again once again you can see that whatever the best fit parameter obtained here. Okay, these are the parameters. Okay, and depending on the calculation you can see that what are the parameters is given here, and the base fit parameters for other equations. There are different equations. First they have taken the condition of the adsorbed phase, and then without the adsorbed phase, these two conditions are going to give you some two different parameters, and they have seen the variations. Now see, this is the variation, how this adsorption capacity with varying with the volume effects, with the pressure. Okay, so this is the volume effect. The right side graphs is going to give you the volume effects. That means it is expressed in depth basis. Okay, so with pressure you can see how the different models is expressed to show you the variations. For the first coal, Pocahontas number 3 coal, the variation is much milder. For the second Blind Canyon coal, it is also steeper but within the range. Whereas for this White Oak coal, the volume effects are much more prominent for the pressure range. Okay, and so this much variation can give you significant error into your adsorption capacity consideration. Okay, that's why the volumetric effect is obviously going to be considered. Okay, now later the other important parameter, you can see that whenever you are going to take the volume effects, you can see here they have calculated the excess absorption and the absolute absorption also. Okay, the absolute absorption is going to be calculated after the volumetric effects are corrected. So you can see this is the volumetric effect which is going to increase with the pressure. So whatever the excess graph you have got, you are going to apply the correction and you are going to see the absolute absorption is there. Okay, this is the absolute absorption. Why absolute absorption coming less? Because you are deducting the effect, the errors. You are deducting the errors with the excess absorption. Okay, that's why this absolute absorption, you can see that with increasing pressure, it should be reaching flat. So this is the case. It is going to reach the absolute absorption. It is going to reach the equilibrium. But for excess absorption, it is not visible. Why? Because there is an individual volumetric effect for all the samples. Okay. So this is the observation I need to show you. This is the and if you read the conclusion, they are going to show you the same conclusions. Okay. The last paper what we are going to discuss is for the Levy et al. Okay. Now Leviatal, it is very a simple paper, okay, a very small paper, only 7 pages, okay. Let me tell you that they have discussed the methane capacities only, and they are going to relate the methane capacities with the coal properties. Again, they are going to do the temperature very less, okay, 30 degrees centigrade, and up to a pressure of 5 megapascal, okay. And they have measured the micropore adsorption with the same low pressure adsorption by the Dubin-Radakovich equation, and they have modeled using the Langmuir volume, okay. Now let us see the results. This is the first result with temperature, Ascending temperature with the methane capacity. You know that the temperature is going to affect inversely. So obviously, with the increasing of temperature, the capacity is going to decrease. Okay. The next is the moisture. Moisture is very much sensitive for the adsorbent capacity. Moisture is very much detrimental. So an increase in moisture content is again going to show the very less adsorption capacity. Okay. Sorry. Next result they are going to show is the capacity of the surface area. They have calculated the low pressure volume adsorption by CO2 micropore adsorption, and with this they are going to calculate that they are going to relate the surface area with the volume. So here you can see there is a positive trend. Here you can see that there is a positive trend. Trend means the more surface area, the more is the adsorbed volume. Obviously, you know that if the surface area is, you are increasing the surface area, you are increasing the very much surface that is going to be applicable for the adsorption. So obviously, it will be going to increase your adsorption quantity. So this is the same case which is happening here. The more number of increasing the surface area, you are going to increase the adsorption volume. That's why the core sample, if you are going to put the adsorption for a cylindrical core sample, at the same temperature pressure, you are going to take the powder sample. So obviously the adsorption will be higher for this powder sample. Why? Because of the increase of the surface area. You are going to break the sample, so you are obviously going to increase the surface area. Okay, that is the main, one of the main parameter to show you the increased quantity of the adsorption. Now here they are going to show the variation with the fixed carbon with the methane capacity. So here you can see that even if the fixed carbon is increasing after some time, there is no such prominent change in the adsorption capacity. But then suddenly, for some type of the coal, there is a very much steep increase of the gas adsorption capacity, okay, even if there is a small variation of the fixed carbon. So there is this different opinion, different observation of the fixed carbon content. It is generally we have taken consideration that the more carbon percentage is going to give you the more carbon, adsorption quantities. But here you can see, and you have seen earlier also, the rank is very much confusing when it comes to the adsorption capacity. The rank, it is not always the simpler case. That means if the rank increases, the volumetric capacity is also increased. No, that is not the same principle. Okay, there exists some different observations also. Here also with the fixed carbon, you can see that there exists some U-shaped relation. Okay, so with some lower, you can see just like the earlier Bulazov sample in the Bush paper. In the Bulazov sample, it has shown some higher maximum adsorption capacity. So here also you can see for some type of coal also you can see the highest adsorption capacity at some lowest fixed carbon content. Okay. The next observation is also for the same carbon dioxide, and here they are going to give you the total carbon content with the DAF basis, and then they are going to measure the methane capacity and plot all the results. So it is going to little bit, it is going to increasing trend. Okay. And let us come to this Langmuir volume. After this Langmuir volume and the Langmuir volume correction with the nitrogen and the carbon dioxide, you can see here, if you take the ratio of the methane and plot it with the nitrogen and the carbon dioxide, compared to methane, with the range of methane, the nitrogen is coming very much less. You can see 10 to 20. With a methane of 15 to 30, it is coming as 10 to 20. So again, there is some lower ratio. But here for carbon dioxide, the volumes are coming from 30 to 50. So again, you can see some 1.5 times or more or less double the effect. Okay, so this is again going to show you the ratio of the adsorption between nitrogen, carbon dioxide, and methane. And this is the variation in the Langmuir pressure. For carbon dioxide, it is not that much important, but for nitrogen, it is very much significant. It is going to be continuously increasing. Why? Because of the different curvature of the isotherm of nitrogen, methane, and carbon dioxide. For carbon dioxide, you have seen that the graph is becoming very much steeper in the initial stage, and then it is becoming very much flatter. But for nitrogen and the methane, it is continuously going to change in a milder curvature. Okay, that's why the different concept of this Langmuir pressure. Okay. So these are all for today, and I'll request you all that if you are having any difficulty, you please see this video again and read at least once for the paper and try to understand the various observations. Okay. In the next class, I'll show you some other papers and I'll discuss some other topics which I have not already discussed. If there is a common topic, obviously I'll be skipping. Okay. Any questions for today's discussion? No questions? Okay. So thank you. And let me tell you again that I'll